we are a group that is scattered all around Italy, more or less, Torino, Padua, Firenze, Napoli. I will briefly explain the context in which we are moving, that is the spectroscopy of the extended solar corona. And I will, of course, talk about the current technological limitation and our idea to overcome the technological limitation. And I will talk about the status of our development of the prototype and the tests that we foresee to perform. So first, which is the framework? Our prototype is thought for as a focal plane device for solar coronas. So we are studying the solar corona. It's thought for coronographic applications, but it's a completely new paradigm in optics. So once the principle is proven, this first prototype, it can easily be exported to many different fields, even beyond astrophysics. I'm not expert of anything that I was saying to Antonio. So if you have ideas of different applications, once I have explained everything, you can suggest, and I'm open to everything. Coronography. The solar corona is the part of the solar atmosphere that is possible to see from Earth, from ground during total solar eclipses, or with instruments that simulate total solar eclipses, like coronagraphs. This is the first solar coronagraph that was invented by Leo in 1932. This is a scheme of his coronagraph. So they had a primary objective that was directly exposed to the solar disk light, and this lens was forming the solar disk image on an cutter that was blocking the solar disk light. So this is what is simulating the eclipse. And then you have the field length that produces the image of the corona. The most critical aspect in designing coronagraph is tail light suppression, because the corona is in the visible more than 6 orders of magnitude fainter with respect to the solar disk. So you have a huge amount of diffraction and scattering coming from the solar disk. And there are two kinds of coronagraph. Many of the coronagraphs that are flying in space now are externally occulted coronagraph. So there is a difference with respect to the very first coronagraph invented by Leo. This was occulted internally. So this was letting the solar disk light entering the instrument. Most of the space coronagraphs are designed with an external application. So you have the solar disk light is not let inside the instrument. We are blocking it before. For example, this is one of the most famous coronagraphs. This SOHO LASCO C2 that is operated since 1995 and is currently producing images. And a triple disc occulter in front of the primary objective. And the coronagraph design has been evolving throughout time. And one of the most, the best performing instrument is now Solar Orbiter Metis that was launched in 2020. I say one of the best, not only because it's Italian, because also I have been working on it and I've been designing the occulting part. And it has a new system for occulting the solar disk. Basically, it's still an external occulted coronagraph, but it's based on an inversion of the actual occulter and the aperture of the instrument. So the solar disk light is let through the instrument, but is then focused out by this spherical mirror that is the actual occulter, and is not the solar disk light is not reaching the primary mirror that is M1 there, that is collecting the solar corona that is coming from a different angle. And then you have the secondary mirror that produces the image on the UV focal plane and on the visible focal plane. And this producing images like this one. There is composite images between Mantis, the gray part, and UI precisely this image on board solar rocket. So we are studying the solar corona. Solar corona, as you see, is a very dynamic environment with explosions, mass ejection, flares, that are evolving on a time scale that is around the hour, let's say. Even less than that sometimes. So, and if you want to investigate quantitatively the physics and composition of the coronal plasma, you need spectroscopic investigations. And the solar coronal spectrum is characterized by several emission lines, many of which are in the UV and EUV parts of the spectrum. Some interesting lines are also present in the visible light in the near infrared. Unfortunately, due to mainly technological limitations, the only coronagraph spectrometer that has continuously observed the extended solar corona in the UV has been SOHO UVCS. It was operative since 1995 to 2009. And of course, it obtained very important results, but probably this one. This is the SOHO satellite. It is currently operating in the Lagrangian point L1 between the Earth and the Sun. This was the design. So it was a coronagraph spectrometer, so it had to block the solar disk light for making spectroscopy. It had a linear slit here, and it had a linear occulter, was out of the instrument. This is the slit that is projected onto the solar corona in order to understand which portion of the solar atmosphere the instrument was able to investigate. And by tilting this mirror here, it was possible to translate the position of the slit on the corona, so that it could be possible to explore different heliocentric heights or different distances from the solar disk center. But in order to explore different polar angles, the whole instrument had to be rolled. So with UVCS, a spectrum of the whole extended corona at full resolution took about 1 day. As I was saying before, all the phenomena that are happening in the corona are on a time scale that is on the order of the hour. So the instrument was taking average spectrum of the solar corona. It did not follow the dynamic of the corona. Of course, he obtained great results. He basically wrote the database of the emission lines in the UV, but on average. So, and here we come with our idea of a circular slit. So no more a standard classical linear slit. Circular slit that can, in principle, achieve the whole spectrum of the corona at a fixed heliocentric height, a fixed heliocentric distance from the solar disk center. The circular slit must be coupled with a circular grating. This way, if you vary the radius of the circular slit, you can explore different distances from the solar disk center. So basically, we are cutting out a degree of freedom. We are going from tilt and roll of the classical spectroscopic case to just a slit radius variation. So we proposed this concept, and we were funded by the National Institute for Astrophysics in Italy in 2023 for a feasibility study. Of course, we have to prove that this new paradigm is working. And the goal of our project is, as Antonio was anticipating, to design and assemble a prototype, a laboratory breadboard, and something that can be tested on the field, probably in Javalambre. And we have the ultimate goal, of course, is to design an instrument that works in the UV and propose it for a space mission in the coming years. So, what do we expect as a dispersion from a circular slit and a circular grating? So, where is the spectrum going? So, if you have a linear slit like this one, you have a spectrum that is dispersed perpendicularly to the slit and to the grating direction. But if you think on circular grating and the circular slit, and you imagine that this is a small portion, microscopic portion of the circular slit, you will see that all the spectra are dispersed radially. So on the focal plane, you will get radial spectra for each source point on the slit. So for each point on the solar corona at a fixed heliocentric height, you will get a different radial spectrum on the focal plane. So this is more or less what we expect to see on the focal plane. These are three source points on the solar slit, on the circular slit. These are different spectra that you will get on the focal plane. This is the scheme of our prototype. So we have, as I was saying in the beginning, it is a focal plane device for a solar coronagraph. So we are not dealing with the coronographic part. We are not blocking the solar disk light. We expect to see only the corona. So this is the coronal light that is coming in. This is the lens that is producing the image of the solar corona on the primary focal plane where the slit is placed. So we have this slit that is intercepting with certain heliocentric height. Then, of course, by varying the radius of the slit, you can intercept different heliocentric heights. And here you have the source points for your grating. Then you have a optics that is collimating the light coming from the source points in order to make it reach the grating. The grating is dispersing the light, and then you have focusing optics that is producing the spectrum image on the focal plane. This is the timeline of our project. So basically, we had to deal with everything from the beginning, from the scientific case to the metal pieces. So we defined the scientific requirements. We decided to go for a visible light range because it's easier to manufacture. As a first prototype ever, we have to deal with something that is easy to manufacture. We know that there is a very interesting line in the visible part of the spectrum. It's the iron 14 line, 430 nanometers. We define the spatial and spectral resolution, the line separation that we had to achieve on the focal plane, and then we had to investigate the two innovative elements: the circular slit with variable radius and the circular gratings. And for both, we had to define a practical way in order to be fast and stay within the timeline of the project, that is 3 years. We had to design and mechanically and optically the spectrometer, build parts, assemble, align, and characterize in laboratory, and finally perform a field test during the 2026 solar eclipse that will be visible here in Javalambre. And we are more or less here. So we almost completed the building, the manufacturing of the parts, and we are about to start testing. So what about the two innovative elements? I'm currently describing the status of the development. So I will go through the circular slit with variable radius and the circular grating. For the circular slit with variable radius, we had some ideas, some of that are exotic, let's see. Both in transmission and in reflection. Let's see first the transmissive functioning. The first idea that we had was a double iris. that could in principle work, but we didn't find a mechanical way of realizing the inner disk. This is easy. The outer diaphragm exists. It not exists. But this part is and small as it must be. The data is a few millimeters. It's very hard to invent. Let's say. We also thought of an inflatable membrane, and a suitable material could be the membrane that are used in angiography, for example. We bought one. We are testing, but we stopped in order to develop, to be practical and develop the actual instrument. But we will do some tests on that as well. And in reflection, that is I think the most viable idea. It's based on digital micromirror devices. These are matrix of mirrors, micromirrors. The dimension is about 6 microns, 10 microns. That can be actuated independently, so they can be tilted independently, one from each other. So basically, you can control the movement of each of the mirror, and if you place them in the right position, you can turn on the shape that you want. You can turn on the slit. This is a test that we did with the DMD that we bought. They are commercialized by Texas Instruments mainly. In this setup in laboratory, we had the laptop with the controller. This is the shape that we wanted to replicate with the DMD. A source that was illuminating the DMD. And here we have the screen with the result. So basically, the laptop was telling the DMD to simulate this shape. The source was illuminating the DMD. The DMD was reflecting just that part on the screen. And this is the enlargement of the screen. But this device can work. And of course, I was thinking of such a kind of a device because very fast it can change the orientation of the mirrors, and you can change dynamically the radius of the slit. But so far, all commercial off-the-shelf DMDs are built with a protective window in front. Plus, the micromirrors are placed in a special lubricant gas. So this prevents us from using it in the UV because the window will block the UV light. Not all hopes are lost because UV DMDs are highly desirable in maskless lithography, the industry for electronic chip manufacturing. And there are many active research that are aiming or developing UV and UV DMDs. So I hope that something will happen in the coming months or years. For the prototype, we had to choose a practical way, so we ended up with a motorized filter wheel that is exchanged circular slit with different radii that are corresponding to this heliocentric height in solar corona in solar radii. So 1.1 means 1 solar radii plus 10%, 1.2, 1.3, and so on. Different slit width. These were manufactured by laser cut on steel, and they're very precise. We also measure them. They're all within the requirements. So we have the variable circular slit for the prototype. What about the grating? The grating is, again, a new device. There are no commercial circular grating with concentric circular grooves. So we have to do design. First, we have actually to find a library in the optical ray tracing program that was able to simulate such a device. We developed our own library, and then we found something that could be adapted, so we used both. But the device has an intrinsic drawback because let's consider, as I was saying in the beginning, the approximation of the spectra that are radial on the focal plane is working better if the dimension, if the radius of the grating is very large with respect to the footprint of the beam that is coming from the source point on this beam. If you think of a footprint, let's imagine it circular, that is produced by the impact point of all the beams that are coming from a single point source on this beam. And we imagine to have this footprint at the top of the grating, let's say aligned with the y-axis. All the impact point, all the beams that are arriving along the y-axis, we see a perfect grating with aligned along the x-axis. But if you move from the y-axis, we will have a component, the direction of the grating that is along the x-axis, y-axis as well. And so you will have a dispersion that is not perpendicular to the x-axis, but as a component that is along the other axis. And so the effect that you see on the focal plane is no more a single point, but is a arch like this. And this is something that we actually saw in the first simulations. This is one of the first designs that we had, and this were the result of the focal plane. So we had all those arches, depending on the intrinsic properties of the plane. We found some, well, actually, we are developing a theoretical model for this effect that we call azimuthal smearing, this drawback, let's say. And I hope the publication will be ready for submission soon. But for the time being, we adopted an empirical solution. As I said, there is a lens that is collimating the light coming from the slit. It's collimating the light to reach the grating. So we are not using a perfect collimation. We are using a slightly converging beam on the circular grating in order to reduce the spot. And we are placing the detector not at the focal plane, but at the minimum confusion. And this is what we are getting spots on the focal plane. The grating has been designed with all the specification. It's a low resolution grating in order to keep the expense low. But we have to prove the principle. We don't have to be super science now. We have to show that the device is working. So we send all the specification to the agency. Now we got the grating. This is the grating for the final prototype. It's 140 millimeters in diameter, so something like this. It was achieved by single point diamond turning technology by this factory in Italy. And this is a technology that, if it's proven, we're going to test the grating in these days, that is fulfilling our requirement. The technique might turn out in the future to be used for machining grating masters, even for linear gratings. And if it's the case, we can think of apply for the grating as well. The grating is not coated, is in bare aluminum. This is a plot of the reflectivity in this. With a standard oxidation of the aluminum is fairly good in the region of the spectrum we are interested in. We are covering from 525 nanometers to less than 700. So we are in this region, and we are always above 890, more than 89, something like that, in reflection. Then other parts of the instrument, the detector. The detector we chose and we bought is the COH vacuum illuminator. It has a pixel size of 6.5 microns, that is even beyond our requirements. So we will have to beam on the detector, a full value of 48,000 electrons. And it has a quantum efficiency that is very good in the region of the spectrum we are interested in. This is the light blue curve here. So the device, the prototype. This is the opto opto-mechanical design, and this is the opto-mechanical design. So we have, as I was saying in the scheme in the beginning, we have field optics that is producing the solar corona image on the plane of the filter wheel where the slit is placed, and all the slits with different radius are exchanged. Then you have the collimating optics that is almost collimating. So the beam, as I was saying, that is likely converging on the grating that is placed here. And you have a parabolic mirror and the focusing optics that are forming the spectrum image on the plane. The parts are machined in different way. This is the part that will be attached to the mount, and in order to have it built in aluminum, they had to manufacture it from a single cylinder that was, we had to drill the single cylinder, so it was very expensive and it was time consuming and so on. So we decided to go for a new technology. It will be 3D printed with the nylon reinforced with carbon fiber. That is almost rigid as aluminum. With this new printer that is available at the Department of Earth Science at the University of Florence. This is, I don't know if you can catch the dimension of the printer, but this is me reflected in the glass of the printer, so it's something like this. Then the back part there will be either printed or covered by a black nylon sheet. I don't know. We have to discuss with Antonio on this part because we went yesterday at the observatory and it's windy. So all the parts that I was thinking to cover with nylon, we have to think a bit better about that. We thought even by installing a tent around the telescope, so maybe that can work. This is another piece that will be printed in a different printer, a Sinter Lisa Pro in Padova, in this material, PA12. This white pattern. The white pattern is supporting the filter wheel. This is a commercial of the shelf Torlabs mount with lenses that are already bought and already there. And that's it for the part, the mechanical part of the instrument. This is the optical design, some details on that. I already described the field optics, the collimating optics, and the focusing part with the grating. The aperture diameter is 30 millimeters. We have a low resolving power, as I was saying. The grating is not designed for high resolution. And this is a way of measuring the spot diagram on the focal plane. This is the semi half of the square in which 80% of the squared energy is on the focal plane. So the lower the better. And we are very good in the wavelength range that we are interested in, that are these ones. So we have very good performance at 530, the iron 49 is. Then we have good performance at argon 11, and then we have not very good performance here, so the light will be more dispersed by the grating uniformly. Then you have good performance again, around 650 here, where the iron 10 is. I must spend two more words on the lenses, on the focusing lenses, these ones here, because they are made in PMMA. They are in their hydrospheric lenses. Again, they are manufactured with a single point diamond turning technique. The company is the same that manufactured the grating. They developed a new technique for manufacturing hydrospheric lenses without much mechanical stress, because you have to hold of course, the PMMA is not rigid as glass. So you risk to deform the PMMA while machining. And we designed a sample lens in order to test if the technique that they developed is good enough for our purposes. And we will test the sample lens that we ordered together with the grating in a preliminary dedicated setup. And if the test will be satisfactory, we will proceed in ordering the full lens itself. About the PMMA, there's performances that are good, comparable to the glass. Actually, if it was not so plastic-like, if it was not so subject to scratches and environmental degradation, the remain would be used to substitute glass for the application, because it can be much easily deformed in exotic curvature, highly aspheric shapes, and so on. So I talked a lot about visible light, but our ultimate goal is to develop a UV prototype, because we want to propose it for space application. Of course, PMMA is good in the visible, but not in the UV. Nothing that is in transmission can be used in the UV, not below 115 meters. So, of course, we have to work with the reflective surfaces to work in the UV, in parallel with the activity. The prototype for the VR prototype, we are developing a high resolution or reflective optical design version of CISS, even for the UV. So, as I was saying, we are here, we have to talk about tests we want to perform. So first, the laboratory tests. They are going to start now. I don't know if they start on Friday. They will start today if everything goes as planned. First, we will perform a morphological evaluation of the grating, the atomic force microscopy in Padova. We have to develop a custom order for positioning the grating on the AFM, because you have to explore something that is not centered. So we have a hole to explore a surface that's the center. We have to position the grating the center. After this, we have to perform optical tests with the sample lens that I was talking about before. And this is the setup that we designed for test. For making this preliminary test, we developed a custom 3D printed bench order for the grating. Then we will proceed, I guess in spring next year, to the integration alignment test of the actual prototype in lab. And then we have to for the eclipse. Why a total solar eclipse? Because with the total solar eclipse, we have not to worry about producing a total solar eclipse. We don't need a coronagraph. We don't need to develop a coronagraph within the budget of the same prototype. So, and we have to prove a principle. So it's good to get an eclipse. Of course, something will be done in the laboratory, but if you have something in the field, it's always better. So it's a practical way of accessing to the solar corona. We have low stray light because we have the best occult ever, which is the moon. Of course, you have a drawback, it is the duration. It's a few minutes, in this case, it's very low duration, it's very short duration, it's 1.5 minutes. And in this particular case, the elevation is 5 degrees on the horizon. There are two pictures, one is not taken by me, this is taken by me at the last solar eclipse in Texas. These are the characteristics. The eclipse, as I was saying, 1 minute and 25 seconds at 5 degrees on the horizon. It's the last part of the eclipse, the best, the greater eclipse is near Ivan, but it's, I guess, as Lapo is teaching, is always cloudy, so nobody will see this except for us. The eclipse setup. We have to define this. Yeah. But okay, CISS is around 20 kilos. Then, in addition, we'll mount a guiding telescope with a small CMOS camera on top of the cylinder. We were thinking of the Skywatcher UQ8, which can be obtained or known by the OPC in Italy. Antonio was suggesting a mount to support heavier weights. Okay, we have to define it soon. The installation site we were thinking about before coming here was this one, close to the JST 250 dome. Yesterday, we had a preliminary inspection at the observatory, and maybe this could be another potential site. Even because in this site we could drill holes around the platform. And so maybe we can install a tank there. It's something that must be discussed. Last, the radiometric model. Of course, we have to be aware of the signal that we can expect on the front plane in order to understand if we are fitting within the time of the eclipse, and which is the kind of signal that we have to detect with the detector. We developed a custom radiometric model. We were forced to do that because the device is pretty new. And there are not so many literature data on the iron 14 line. We only found this contribution of Key in 1997. The visible light corona is well known and is uniformly dispersed by the grating, but you have to take into account the visible light corona as well, because it's pollution in your case, but you have to take it into account. This is the scheme of the instrument. So we are interested in measuring the light that is going into a portion of the slit that has a slit width as height, and what is going to be imagined in a pixel on the focal plane. So basically, we make a projection of the pixel through the optics onto the slit plane. So we need a zoom factor that is introduced by this optic, and the dimension in which we are interested is the pixel dimension divided by the zoom factor. So with this radiometric model, we have a preliminary result, which is this one. We have something around 500 yens at 1.2 solar radii, yen per second per pixel. So we will have short exposures with the smaller slits, and then the signal is rapidly decreasing. We have to increase the exposure time by moving up in the corona. And I think that's it. Yes.
Thank you very much, Federico. Question? I have one.
Yeah.
Why not using fibers instead of a circular?
Yes, that's an idea, but you can use them in the UV. And you want to improve a principle that is working in the UV as well. So you must use something in view. Although you have, in this case, transmission optics. But once you have transmission optics, you translate them in reflective optics.
Yeah. With this circular slit that you are proposing in the filter wheel and I mean the system that you just proposed, would that make any sense to do some tests in any day without an eclipse? Because in theory you are only allowing the coronal light going through the slit,
you can make measurements with the moon.
Reflections.
You can make measurements with the moon that does more or less the same irradiance of the eclipse corona, but you cannot do measurements with the sun because you have stray light everywhere. In order to measure what you want to measure, you have to block the solar disk, and you have to have a coronagraph.
Yeah,
in front.
to have the
You need the coronagraph. Otherwise, you cannot do the.
so just
Straight light is
making an effort on anti-reflective coatings both on the circular slit
you
and the
don't do
lenses.
anything with anti-reflective coatings. Straight light is huge.
Too many orders of magnitude.
Yeah, no, it's huge. With ground-based solar coronagraph, you can only observe the corona that is very close to the needle. Otherwise, you have straight light.
Then I have to, I mean, this is my curiosity. So the PMMA lenses that you mentioned with very low reflectivity, this is without any kind of anti-reflective coating. This
Nothing,
is only
just the plastic. Yes.
Only the plastic.
I think it's the same material of eyeglasses. Eye lenses. I don't know the eye lenses. Maybe, yes. I don't know. I don't find it anymore in my presentation. It's here. Yes. Yeah. It's... No coatings. No coatings. So I found this contribution here. This is fairly recent. But of course, we cannot use in space application because the craze is going to the grade in a week.
Well, this is very interesting for a prototype.
For laboratory application in the visible, I think it's a viable way of performing things.
That's curiosity. Does the spectral resolution changes with the heliocentric radius of the circular slit?
Yes, the plot that I was showing was for the inner field. I think it's 1.2 solar radii. They are degrading a bit, but they are more or less in the regions of the spectrum we are interested in. We optimize the design in order to keep it more or less at the same level.
Yeah,
so it's varying, but not so much. We are going from, I say, 7 to 9 in this case. So it's more or less there.
Thank you for the talk. Very far from the usual thing that we have, but it's very interesting. So, given the short duration of the eclipse and that you need to change the filter wheel, how many radius do you think?
I hope to.
Assuming that everything goes perfect. Okay, that was the.
I don't think we will make more than two because, of course, we will take some more than one experiment. So you want to be sure.
Yeah.
Okay. I have another question. The prototype does not measure polarimetry, right? But the full instrument will. How will this be done? The half lambda.
With what? We want
how
we won't measure polarimetry. We want just the spectrum.
Okay.
We want to isolate the line.
Okay.
Do you have a plan B if the day of the eclipse gets cloudy?
Wait for the next one.
It's pretty soon. I mean, 1 year later, you can
1 year. 1 year, yeah. We have to get the funds for that, but we already applied for that. So let's see. I don't know.
What about stratospheric globes?
What?
Stratospheric globes, like
the balloon?
Yeah.
He's the expert one. Actually, tomorrow you go to launch one. But also for that you have to apply for fund. You have to write a proposal. We didn't do that. We applied for UV version of this, and I think we are in a good position now in the ranking. But we'll see. I cannot say that we will be fun. I hope so. Let's see.
No questions? No? Thanks again, Federico.
Okay.